Welcome back to Tech 240 for Wednesday, January 27th. In this video, we're going to talk about power and energy in general, and then also talk about power and energy in the electrical domain for electrical circuits. So we'll talk about that, and we'll do an example problem where we're calculating power and energy for components in an electrical circuit. And then we'll talk about Lab 4. Lab 4 is going to be done partially in Tinkercad, so it's kind of like Lab 1 and Lab 2 in that respect. And that's about it. So let's go ahead and get started by talking about power and energy. So first I'm going to give you a couple of definitions, and then we're going to talk through them. So first of all, let's talk about energy first. Energy is the ability or capacity to do work. All right, and work, yeah, there is actually a technical definition of that. I'm not going to sort of muddy the water with the definition of work. If you think back, maybe you've taken a physics class. Work is a force moving through a distance. But for us right now, all we really need to think about is work is something useful. Just think about it that way. All right, so if I had something that had potential energy, let's say I took like a brick or a bowling ball or something, and I lifted it from the floor up to over my head. And I know you can't see me right now, but I'm pretending like I'm lifting something really heavy from the floor up and over my head. And if you think about what kind of energy I just gave that heavy object, I'm sure you remember that I just gave it some potential energy, right? So it has the ability or capacity to do work. How? Well, I could drop that heavy thing and it could hit my foot and it could break my toe. That might not be useful to me, but it does meet the technical definition of work. And maybe you might think it was useful if you watched me break my toe from dropping something heavy. Or maybe I could take that heavy object and tie a string to it and then run it through some pulleys, and then as it drops down to the floor, have it spin a turbine or a generator or something like that. Or as it drops, maybe have it, through a lever or a pulley or something, lift something else up that I want to be lifted up. So it certainly has the ability or capacity to do work or something useful for us. The units that you'll often see for energy, some of the most common ones are calories and BTUs, or British thermal units, or joules, or watt hours, or kilowatt hours, which are just 1,000 watt hours. So for us in the electrical domain, the most important ones are really going to be watt hours and kilowatt hours. These are the ones that we're going to use repeatedly to measure electrical energy in this course. And if you look at your electric bill for your apartment or for your home, you'll see that your electric bill is measured in energy units of kilowatt hours. And you will probably pay, depending on where you live, probably somewhere between 10 to 13 cents per kilowatt hour if you live in Illinois. Mine is probably right about in the middle there. I probably pay about 11.5 cents per kilowatt hour. At least that's for any energy that I buy that I don't produce with my rooftop solar system. I don't know if I've mentioned that in this class before, but I do have a rooftop solar system on my house. Had it put in about 2 years ago. Really happy with it. And maybe I'll talk a little bit more about solar energy a little bit later in the class. But for now, let's suffice it to say that kilowatt hours is the most commonly used unit to measure electrical energy. All right, so when I was talking about energy and I was talking about raising a heavy object above my head, at no point did I talk about how quickly I moved it over my head, right? So I didn't talk about the rates at which I lifted it over my head or how fast I was giving it that energy. Because energy doesn't it doesn't matter. It doesn't matter how quickly I lifted that bowling ball or heavy object above my head. Once it's up there, it has a certain amount of potential energy, regardless of how fast I gave it that potential energy. So when we talk about how fast we gave it that energy, or the rate at which we increased its energy, that is a metric called power. Power is the rate, and I want to emphasize that. Power is a rate at which energy, oops, I didn't mean for the comma there, energy is produced, I'm going to put this in quotes, produced, consumed, or transformed. And if we were in person, I would ask you, why do you think I put these in quotes? And probably some of you would know why. And that's because the first law of thermodynamics tells us that energy cannot be produced or consumed, only converted from one form to another. So really, all we're talking about doing technically is transforming it from one form to another. Say from electrical energy to kinetic energy, or from electrical energy to thermal energy, or from chemical energy to thermal energy, or chemical energy to kinetic energy, potential to kinetic, so on and so forth. The list goes on and on. So really, all we're doing in any of these processes, you know, in a generator or a motor that we're going to talk about in the second third of the class, we're just transforming one form of energy to another form of energy. That's all you can really do. And units for power, I'm sure you've heard of horsepower before. We could also use BTUs per hour, because look, BTU is a unit of energy, but power is a rate. So if I take BTU and I talk about BTUs burned per unit of time, all of a sudden that's a power. That's a unit of power. So I could say BTUs per second or BTUs per day. Any of those would be a unit of power, but BTU per hour is probably the most common one that I see to rate furnaces or say gas grills or something like that. That's pretty common. And the most common one that we are going to use, I'm going to leave it like that because it's the watt, W-A-T-T, but I'll leave it like that because that's the way we usually write watt. Or kilowatt, and that's the way we usually write kilowatt. It's just K-I-L-O-W-A-T-T, but that's the way we usually abbreviate kilowatt. So in our class, in Tech 240, in electrical domain, the watts and the kilowatts are the most important units for us. All right? And we'll talk more about how we calculate that and that momentarily. All right, so we said that power is a rate. So from this, we can actually turn this qualitative description into our first equation. And we can say that power is equal to energy per unit time. So I can just divide by time, or the change in time. I like to write delta t. So time 2 minus time 1. How long did this process take? All right. So that's an equation that we can use, or we can do a little bit of algebra on this, and probably the way that we see it more commonly is to say that energy equals power times time. I'll write it like this. Okay. These are both useful and both important. They're really not two separate equations. It's really just one equation that has been rearranged. And one thing I want to point out about this is that these are useful so long as we make an assumption about power. And let me illustrate that. All right, so let's say that we plot power versus time. Power in watts versus time in hours. For something really simple, like, let's make it super easy, like 100-watt light bulb. All right, so here's 100 watts. And I'm going to say this 100-watt light bulb is turned on for 2 hours. All right. So I plot that, and it's on for 2 hours. Now, a 100-watt light bulb consumes 100 watts of power. All right. And it doesn't change. So it's not like it's consuming 110 watts sometimes and 90 watts sometimes. It's just constant, and it's consuming 100 watts. Now, if we want to calculate the energy here, we have this equation, energy is power times time, and I want you to recognize that all we're doing here is calculating the area of this rectangle. So the area under this, quote, curve, this is not really a curve, it's a line, but the area under here is the energy. All right, so that's the energy. So when you're calculating the energy, this is a good thing to know. Energy is equal to the area under the curve of power versus time. All right, let me give you another example. It's not quite that straightforward. And now I'm going to plot, still the same axes, power. Let's do it in kilowatts this time. Still just power though. And this is time. Let's say in, well, it really doesn't matter. Let's say in minutes. All right, so I'm going to get a different unit of energy, but it's still energy. It's still power on this axis and time on this axis. So you can probably guess what I'm going to do, maybe. But I'm going to plot power versus time. This time I'm going to plot it for my electric motorcycle. And maybe sometime, normally in this class, normally I bring in my electric motorcycle to class at some point and just point out the different components, and also point out that we're going to talk about pretty much every single aspect of the electric motorcycle during TEC 240. And by the end of TEC 240, really, you are probably qualified to undertake a project like that. You can do a conversion, and what you don't know, you'll learn along the way, but you'll have the basic knowledge to do a project like that. Anyway, let's say we plot the power consumption of my electric motorcycle as I'm driving from my home to my work. All right, so it starts out at 0, and then I accelerate, so the power goes up as I'm accelerating, and then I'm going to decelerate, so my power goes down. I come to a 4-way stop, and then I accelerate onto the road near my house that has a speed limit of 45, so my power goes way up, and then it's constant for a while, and then it drops a little while, maybe I'm slowing down, and then I'm going to coast for a while, so it continues going down, and then I slow down, and then I accelerate again, and so it might look something like this. So the same point holds up here. Energy is equal to the area under the curve of power versus time. So if I calculated all of the area under here, this is equal to the energy. But how do we do that calculation? Well, there's kind of two answers here. One answer, the simple way, is to saying, well, I don't know. I don't know what this is, but I can get a pretty good idea if I estimate the average. So the average power is probably something about like this, right? And I know how long it was. So I can get a reasonable estimate of the energy consumption if I take the average power, say this is PAV, that's the average power, and I multiply that times time. That'll give me a pretty good estimate of the energy. So you can either do that, or you can do some calculus. Likely you're going to need some computer software to do this. So you can either, when you're doing this calculation, you're either, let me say 3 different possibilities here. One possibility is assume constant power. That's the case in our 100-watt light bulb. Right? That's one way to use this equation. You're assuming that the power is constant. The second way is to use an average power. Because that'll work. The area under this curve of the average power, it would be the same as the area under the curve of the time varying power that's changing over time. Or the third option that we can't really use in this class, it's beyond the scope. You can use calculus. Use calculus, specifically integrals. Calculus, integrals. The integral in calculus is exactly the area under a curve. That's what an integral is. So we're not going to do that in this class because that's just beyond the scope of this class. But if you had some computer software and you plotted the power over time, then a computer could calculate the area under this curve, which is also equal to the energy. So in our class, we're going to use one of these two. We're either going to make calculations assuming that the power is constant. Let's say for, well, in any electric device or any device, you can assume that the power consumption is constant or roughly constant. Or if you can get some idea of what the average power is, then you can do this calculation and you can get a pretty good idea of what the energy consumption is. Okay. All right, so this is in general terms. This is all, it's all true in the electrical domain, but this is not necessarily specific to the electrical domain. But to make it specific to the electrical domain, in the electrical domain, we have an equation that I'm pretty sure that you've seen before. If you haven't, that's fine. You can pick it up right now. It's not hard. The power dissipated by component in is equal to the current through component in multiplied by the voltage drop across component in. So once again, don't just write P equals IV, right? P for components, whatever subscript you want to use here. P1 equals I1 V1, or P2 equals I2 V2, things like that. Be specific. And the units that you're going to get, be careful of your units. Power in watts is equal to current in amps times voltage in volts. So if you take an amp times a volt, you get a watt. So I recommend, just like for Ohm's law, I recommend converting into amps and volts before doing this calculation. And then if you get a really small number, then by all means, if you want to, convert it into milliwatts or microwatts. Or if you get a really big number, and you want to, by all means, convert it into kilowatts or megawatts or gigawatts or terawatts or whatever unit you want to use. But use these base units. It'll make things easier. All right, so, and then of course, we have our energy equation, and that's actually the same. So we have this equation for power and then energy for component in. The energy dissipated by component in is equal to the power dissipated by component in times how long. Actually, I'm glad I did write this out. This brings up probably one of the biggest ways that students get confused here. So energy equals power times time, right? So power, I'm going to rewrite this over here just to give myself some more room. Energy is equal to power times time. All right, so power is going to be in, let's say, watts, and time is going to be in, let's say, hours. It could be in minutes, but the most common unit would be hours here. So what do I get for energy? What is my unit for energy? Well, we can cheat. We already looked up here, so you already kind of know. But one thing I see a lot is that students are doing this calculation, and I don't know how. I'm not exactly sure how they come up with this, but one thing I see a lot is a unit of watts per hour or kilowatts per hour. And you can see right here that doesn't make sense. If you take a watt times an hour, you're not going to get a watt per an hour. That's a division sign. You're not going to get watts divided by hours when you multiply watts times hours. All right, so in fact, I will tell you, in this class, in TEC 240, if you ever, in any of your answers for any of your equations, come up with these units, it's wrong. So you should go back and take a look at your math and figure out what happened. When you multiply watts times hours, the units that you should get are watt hours. All right. Or if you want to, as long as you're, be real careful, I'd probably recommend just putting them into base units, but I'll admit that sometimes I'll just leave that in kilowatts, and I'll take kilowatts times hours, and then you get kilowatt hours. Not kilowatts per hour, but kilowatt hours. Okay, believe me, I see this a lot, and I see these units a lot in students' answers to quizzes and exams. So be careful. Okay. All right, let's do an example, and then we'll call it a day. So let's do an example problem where we have a 10-volt power supply, and we have two resistors in parallel. R1 is 10 ohms and R2 is, let's say it's 1,000 ohms or a kilo ohm. All right, and we want to find, well, let's say all we really want to know, well, let's say that this circuit is energized for 2 hours. Okay, and we want to find what is the power dissipation of resistor 1, what is the power dissipation of resistor 2, what is the total power dissipation in the circuit, and we want to find the energy dissipated in resistor 1 over those 2 hours, and the energy dissipation in resistor 2, and the total energy dissipated by that circuit. All right, so this is a pretty straightforward example, but if you can do this one and you can do lab 1 and lab 2, then I'm confident you can do more complicated examples. So first of all, study this circuit for a minute. Think about what this circuit represents. And of course, we know this is a parallel circuit where we've got these two resistors in parallel. What do we know about parallel circuits? We know that the voltage drop across them has to be the same. And in fact, right here, if I used my multimeter, I would know that the voltage drop across resistor 1 is equal to the same as the source. So the voltage drop from here to here is 10 volts, and the voltage drop from here to here is 10 volts. So I already know, just by looking at this, I already know that V1 equals 10 volts, and V2 equals 10 volts. It didn't ask for them in the problem, but I'm going to write it down because I might use it later. So I want to get power, and I know the equation for power in the electrical domain is current times voltage. And now I know the voltage for both of them, but I don't know the current going through here. Okay, but I do know the value of the resistances, and I know the value of the voltage drops, so I can use Ohm's law. And I can find I1 equals V1 divided by R1. V1 is 10 volts, R1 is 10 ohms. So I1 equals 10 divided by 10 is 1. A volt divided by an ohm is an amp. So I know I1 equals 1 amp. Now I do the exact same thing for I2. I2 equals V2 divided by R2 equals 10 volts divided by 1,000 ohms. So to divide by 1,000, I just move the decimal point 3 places here. So 1, 2, 3. So I should get 0.01 amps. But you know what? I like to double check. Better safe than sorry. So when in doubt, just go ahead and plug it in. Okay, see, so I was right. So I just feel better about that now. So I was confident before, but now I'm real confident. So I2 is 0.01 amps. And now I know V1 and I1. I know V2 and I2. So now I can find these values of power. P1 equals I1 V1. The current through resistor 1 is 1 amp. The voltage drop across resistor 1 is 10 volts. 1 times 10 is 10. An amp times a volt gives me a watt. So P1 is 10 watts. Now for P2. P2 equals I2 V2. I2 was 0.01 amps and V2 was 10 volts. And when I multiply something times 10, I just move the decimal place 1 point to the right. So now I have 0.1 watts. Better safe than sorry. 0.01 times 10 gives me 0.1 watts. P2 is 0.1 watts. All right. Now, to get P total, all right, there's an easy way of doing this, and there's a slightly more challenging way of doing this. The easy way of doing this is to say, well, if I'm dissipating 10 watts there and 0.1 watts there, then all I have to do is add up the power dissipation. And that's a general rule. The power dissipations add. I'll write that down. That's a good thing to know. To find P total, add up all individual power. I'll just write it like that. All individual power dissipation through each component. All right. So I already know it's going to be 10 plus 0.1, which is 10.1 watts. But why should you believe me? I think I should probably do this just to prove it to you. All right, so let's do it. Let's find R total. So 1 over R total. I don't know why I switched colors, just to mix things up. 1 over R total equals 1 over R1 plus 1 over R2. All right, so I'm going to take parentheses 1 divided by 10, close parentheses, plus parentheses 1 divided by 1,000, close parentheses. All right, so now I've got this value, then I take the inverse of both sides, so I take 1 divided by what I just calculated, and that tells me that R total gives me 9.9. You know what, I'm going to keep a couple more sig figs because I don't want to get too much rounding error here. So I didn't show all these steps here, but hopefully at this point you're comfortable with that. R total is 9.90099. All right, I'm going to keep that many sig figs for now, even though it's ridiculous to talk about a resistor that has that many sig figs. All right, so that's what my total resistance is. And that makes sense because that's less than my smallest resistor, right? If I'd come up with an answer that was like 10 point something or 11 or anything bigger than 10, I would know I made a mistake. Okay, so now I got R total. Now I want to get I total equals V total divided by R total. V total was 10 volts. R total was 9.90099 ohms. We can take 10 divided by 9.90099, and I get 1.01000001. All right, I'm not going to keep quite that many sig figs. 1.01. And then I'll write, I kept 5 digits past the decimal before, so I'll do that same thing again. 1, 2, 3, 4, 5. All right. So that's good. That's my I total. And, oh, I can already see this is going to, I think it's going to work out. All right, so I have my I total, I have my V total, that was just 10 volts, so my P total equals I total times V total. I total was this, I forgot my units, there we go, 1.01000 amps. V total was 10 volts. And when I take anything times 10, I just move the decimal point 1 over to the right. So I get 10.1000, but at this point, I'm just going to truncate that watts. All right, so we just proved it. If you didn't already believe it, now hopefully you do. But to find the total power, all you got to do is add up the individual power dissipation in each of the components, and it actually doesn't matter if they're in parallel or series. You just add them all up, and that gives you your total power. Okay, the next part, we're not quite done, but the next part is real easy. Need another piece of paper. I'm running out of room, so we need our energy. So our energy is equal to P times delta T. So the energy dissipation in resistor 1 is equal to P1 times delta T, which is equal to power 1 was 10 watts times delta T. Well, it was energized for 2 hours, so my time was 2 hours. When I take 10 watts times 2 hours, I get 20 watt hours. And you can abbreviate it like that, WH. If you want to write the little RS, that's okay too, but that's more common. WH is more common. So 20 watt hours. E2, the energy, and by the way, this energy is dissipated in what form? Heat, in the form of heat. Resistors dissipate energy in the form of heat. So this is P2 times delta T, which was 0.1 watts times 2 hours. 0.1 times 2 is 0.2 watts times hours, gives me watt hours. 0.2 watt hours. All right, energy is the same way as power was, in the sense that we can just add these up. All right, but you don't have to take my word for it. We can do this is a simple calculation. We could just add these and say, all right, if I dissipate this much energy here and this much energy here, then my total energy must just be this plus this, which is 20.2 watt hours. But you don't have to take my word for it. Here's the calculation. E total equals P total times delta T. P total was 10.1 watts. Delta T is 2 hours. 2 times 10.1 is 20.2. Watts times hours gives me watt hours. So they match up. E total here equals E total there. All right, so that's basically power and energy in the electrical domain. Hopefully that makes sense. Let me know if you have any questions. And now let's just talk through lab 4 real quick. It's on page 27 in your lab manual. And this is pretty straightforward. If you got through lab 1 and lab 2 without too many hiccups, or even if you did have hiccups, if you eventually figured out how to do lab 1 and lab 2, then I don't think you'll have many problems with lab 4. You're going to do this in Tinkercad, and you're going to take a bunch of measurements in Tinkercad. Notice that in Tinkercad, you cannot measure the power directly. Instead, what you have to do, you have to measure the voltage drop across each component, and you have to measure the current through each component. So like I showed a week or two ago, you got to break the circuit here or here, and here or here, and here or here to find the current through resistor 1, through resistor 2, and through resistor 3, respectively. Okay, and then once you find, by measuring, in this example, don't calculate it. I want you to actually measure it. It says measure. So do this in Tinkercad. Measure the voltage drop, measure the current flowing, and then calculate the power dissipation. So calculate the power dissipation in this column after measuring these things in these columns. Okay. All right. Here, so if you were doing this in real life, one of these resistors would get really hot. And if you think about this, and maybe after you do these calculations, maybe you can see why one of them is going to get really hot. Remember, the way that resistors dissipate power or dissipate energy is by converting electrical energy to thermal energy or heat. So if it dissipates more power, that means it produced more heat. So whichever one is dissipating the most power, that's the one that's going to get the hottest. All right. Here's another interesting thing to consider. There's different sizes of resistors that you can buy. You can buy 1/8 watt resistors or 1/4 watt resistors or 1/2 watt or 1 watt or 2 watt or 5 watt or 10 watt. Those are all fairly common sizes. The difference between these different resistors that are rated for different power is basically the size of the resistor. So 1/8 watt resistors are really tiny. They're little bitty little resistors. No matter what the actual resistance value is, they're all really tiny little resistors. And they're not designed to dissipate much heat before they just get too hot. And eventually they could actually catch fire if you left them energized for too long. As you get larger and larger power capacities, they're just physically larger. They're more robust. I've got a bunch of like 10 watt and 20 watt resistors in my lab, and they're just pretty big. They're just big resistors, so they're capable of dissipating more power without destroying themselves. Here in number 4, it just says calculate. So actually in lab 4, the only circuit that you need to build in Tinkercad is this one right here. So when you submit lab 4 on RegiNet, just like in lab 1 and lab 2, take the screenshot of your circuit that you built in Tinkercad. Make sure you have changed your file name to your last name space lab space 4 and include that with your upload. So these are just calculations. These are also calculations with power and energy in the electrical domain. Keep your units and work slowly all the way through these. A couple of these might take a couple of different steps. So just think about what it is that you're calculating and how you're going to do that. Let me give you a quick sample calculation that might help you. Like I said before, the way that you purchase electricity from your utility is in units of kilowatt hours. So let's do this a little bit in pen. This is just an example that might prove helpful in one or more of these. All right, so let's say you calculate that you have consumed, I don't know, I'm making up a number here, 800 kilowatt hours per month. And let's say that your utility company is going to charge you, I don't want to see, what does it say here, 8.2 cents? Let's say that your utility company is going to charge you 11 cents per kilowatt. All right, so 11 cents, you write that like this, that's 11 cents per kilowatt hour. Kilowatt hour is the unit of energy, 11 cents per kilowatt hour. Okay, so now your units of kilowatt hours cancel out, And now if you punch into your calculator, 800 times 0.11, I get $88 per month. Don't forget this unit down here. All right, so keep your units. What I really want to stress here is as you're doing these calculations, a lot of times I see students just writing down numbers and multiplying like 10 times 13 times 120 times 240 times 8. And I look at that and I think, I have no idea what you just did there. I can't even help you because I have no idea what these numbers represent. So my strong recommendation is to keep your units and then follow along with your units and cancel out your units like I just showed here. And if your answer ends up in units that are reasonable, then you probably did the question correctly. All right, so if I was trying to calculate the cost per month, and I calculated that I use 800 kilowatt hours of energy per month, and my utility company charges me 11 cents per kilowatt hour, then these cancel out, and I end up with $88 per month. And if the question was how much does it cost me per month for electricity, then that would be the units that I would be expecting to see in my answer. So my point is just keep your units and follow along and cancel out units and be careful. Okay. Page 29 is part of Lab 4, but it's the last page of Lab 4. After this, on the next page, there's some circuit calculation problems, and those are not part of Lab 4. So this is some more practice calculating, well, circuit calculations as well as calculating power. Notice, first of all, it just says calculate, so you don't need to put these in Tinkercad. Second of all, notice that on a few of these, here and here, there are some units or some values that are given over here. And you won't be able to solve the problem unless you know some of those values. All right. All right, so with those, you should be able to solve for the voltage drop across each component and the current through each component and the power dissipated by each component. Okay, so that's going to wrap things up for today. I think this topic was quite a bit more straightforward than KVL and KCL, but keep crunching and practicing through those problems, and let me know if you have any questions or need any help with any concepts. I'm always happy to help you out. I love talking about this stuff. It's great. So really, honestly, I do. And so if you have any questions, I'd be more than happy to talk with you about it. So let me know if you need any help. Otherwise, good luck on the labs, and I'll see you next time. Have a good week.